level mismatch.
Okay, good morning. This time we're live, I hope. Alright, this is second lecture of week 4. Where are we at? We're going further into memory, how you access memory, what you do with it, how arrays get stored in memory. So that's going to be our topic for all of today. And it's next week's lab exercises. So this week's lab exercises are really about, well, getting to know the MIPS, getting to know the tools, and branches. Branches, I guess, would be the biggest focus of this week's lab exercises. Branches, syscalls, yeah. The focus of next week's lab exercise will be accessing memory, working with things like arrays at the lowest level. And the week after, which will be after flexibility week, the focus will be function in the labs. So, what else is happening in the course? Assignment 1, where it's been merged into the main repo. It's not yet available. I haven't actually had a chance to look at it, but it's close to go, which doesn't yet, it's no point, I don't want to release it yet because I don't like releasing assignments until you've seen what you need to know in lectures, and you certainly need to see what's in today's lecture. We might try and get it out for people to have a look at before next Tuesday's lecture, and we'll give you a bit of an intro next week, certainly, to the assignment. I'd be setting aside significant amounts of time, week 6, I guess, round week 6, to work on the assignment. There's going to be a lot happening. Well, there's a lot happening in the course right now. It's a little sad in New South Wales as we're sort of COVID restriction days are heading up. With 70 and 80%, you've actually got more and more work happening. So, sorry, you may have to wait until after the end of term to enjoy your new freedoms, whatever they are. All right. So, what else is happening? The weekly test, our first weekly test. If you haven't done it, you've got to do it by 9 o'clock tonight. So it takes an hour. So set aside an hour later this afternoon if you haven't done it. Please, if you haven't done it, please do it. I think we sent out a reminder email. We tried to send out a reminder email to people who hadn't done it earlier today. I think that's all that's happening in the course. All right. So let me switch over to system lecture slides, maybe. Oh, sorry, I've been browsing way ahead. So, all right. So we talked about memory. I'm not sure I gave you a really good explanation, a really clear explanation yesterday. We'll recap a bit of it, and then we'll dive into particularly how arrays work. That's how arrays work with memory addresses is going to be the focus of today's lecture. First, I'm holding here, there is a memory chip. So, well, really it's a memory stick. It's got, I'm counting 16 chips on it, but this is what you'll see if you pull apart your laptop or your desktop or maybe your phone. In some of those cases, almost definitely on your phone, the chips will actually be soldered, it won't be on a separate board, they'll be soldered onto the main board. Elsewhere on the same board will be the CPU. Here's an old CPU, which is some square millimeters of silicon with lots of wires connected to the outside world. How do the memory and the CPU talk? And it's actually pretty simple. There are two operations: either get the value of memory or change the value of memory, load or store. A load operation, the CPU specifies an address and gets back from the memory whatever's in the byte at that address. A store operation, the CPU specifies an address and a byte, and memory changes that byte to have that value. So that's the two things with memory. Sadly, the real world is always more complicated. We mentioned a couple of ways it's more complicated. For efficiency reasons, things called caches often sit between the CPU and the RAM. We don't have to worry about those, but they don't really change the meaning of these things. You do have to worry that you do have to learn about them eventually after this course. If you want to understand efficiency of programs, and also these days security of programs, you have to understand caches. But not for this course, not for this course. The other thing is, I'm saying, you know, CPU, memory, separate things. But if you're doing embedded programming for the sort of hardware we put inside devices, often they'll be on the one chip to save money. So, but that doesn't really change our picture for our things. Still the same fundamental operations are happening. One more piece of complexity. Sorry, I thought I'd turned the sound off. I tried to turn the sound off for those things. One more piece of complexity. Memory load and stores may be more than 1 byte. So on the MIPS, they can be 1, 2, or 4 byte operations. So they can load or store 1, 2, or 4 bytes at a time. That's sort of pretty typical. You might be, I guess, an interesting thing, a crucial thing is, well, can I load and store a bit? Can I say to the memory, change just the 7th bit of byte 153? No, you can't. Generally, memory is byte addressable, meaning that you can't address it, you can't select and do operations at a lower level. So we're generally always talking about bytes. There's some weird terminology here. 4 bytes gets called a word often. And why am you saying, Andrew, if it's why don't you just say 4 bytes everywhere or 32 bits? Because I know you'll be looking at other resources, and other resources on the internet often use the word. It's very common to mean the natural unit of size on a computer. You might also see half word for 16-bit quantities. I don't know if we'll be writing any code that manipulates 16-bit quantities. We'll be writing lots of code that loads and stores 32-bit quantities to RAM, and some code that stores 8-bit. So 1 bytes and 4 bytes. Now, the MIPS is a CISC. Sorry, the MIPS is a RISC, a reduced instruction set computer. So it's the load and store the specific instructions to access memory, and only those, which makes everything easier for you to understand. If we're talking about a byte, it's LB and SB. If we're talking about 4 bytes, it's LW and SW. There is an unsigned version of LBU if you want to load a byte, assuming that it's unsigned. And there's the 16-bit equivalents as well. But I guess those are the 5 instructions there I've circled. They're the ones you want to get across. You understand those, that's all you really need to understand. Alright, let's move on then. There's in raw C, and there's the bit patterns. Let me try and stop these. I tried and stopped these notifications. Apologies for the notification sounds in the audio. Maybe that will stop them.
I don't actually think we're hearing the notification sounds. I don't think they're actually.
Oh, not coming through. Oh, and I've been worried about this for weeks. Thank you, Dylan. You're a load off my mind. All right, let me go back to here are the bit patterns that are the actual. I like this. I like 1521 students to eventually understand the raw bit patterns, to think about what's actually in the instructions that the silicon runs. This is what the course is really about, knowing what a bit of silicon like this can actually do. These are the things that a real MIPS CPU can actually do. Given this pattern, it can do that. Given this pattern, it'll do that. So understanding those raw bit patterns, and the MIPS is a lovely architecture. It's really a thing of beauty if you explore into it. So understand those bit patterns. Maybe you don't have to do it today, though. It's not understanding the bit patterns is not necessarily a route to getting the lab exercises and load and store working. It might be a better path to play with load and store, do the lab exercises, then come back to the bit patterns, and they might make more sense that way. But which one we pick? We'll pick load byte. So load byte specifies a register containing an address. So there are 5 bits to say use whatever values in this register, any one of the 32 registers on the MIPS, as the address to request a byte from memory from. and it specifies a second register, that's where to put the byte. So that says go off to memory to this address, whatever value you find there, put it into that register. You're saying, well, what about these 16 bits here? They're an offset, so that you can say get this, go to the address in this register plus or minus this value. It's a signed value, so it's an offset, and we'll see why that's useful later. It's not needed for what we're about to do though. So those bits will often be 0. This is what we almost never do. This is saying, oh look, go to that address. I specify the address I want in the code. I'm talking about that address. We almost always use labels instead and let the assembler take care of what value of the exact address. That works so much better for our programming. But that's valid code that will load and store a byte, and you can run that if you haven't already. The assembler has directives saying set aside bits of memory for me. So this says set aside 18 bytes of memory. And what we'd normally do in our coding is say to the assembler, set aside 18 bytes of memory and associate label A with the first address of it. Then in my code I can use the label A and refer to it. We can also initialize it. So this actually sets aside 12 bytes of memory initialized to 1, 3, and 5. And we can also initialize it to ASCII values like that, which is key for writing up messages. That was lovely. There are particular regions. The text region is generally where we put instructions. The data is where we store values we're going to change. It's a little more complicated that in the real world, in the real programming, but not a whole lot. That's the fundamental thing there. All right. So this is this program is normal, typical, good, except for one thing. All right, it stores a single byte in RAM. You wouldn't normally do that because you don't need to. A 1 byte value you could just keep in a register. What's the point of storing it in RAM? So you could just keep it in a register. So the code's silly in that respect, but otherwise it's normal code. It says set aside 1 byte, label it X. When I need the address of X, I do it there. And there's a weird thing that doesn't have a really good reason, but if I want to get the value of a label into a register, I don't use LI, I use LA. I actually don't quite know why. Lots of assemblers do that, so maybe it's just for historical reasons. So I guess it's sort of readable. All right. Let me recap here. Ooh. Now I'm lost. Where's my Indianness code? Well, I can go to it anyway. And I showed you this gem of code in the last lecture. This is a C program that stores 4 bytes and then says, give me a pointer to those 4 bytes. Then says, oh, no, pretend that's a pointer to 1 byte. Get that byte and print it out. And you're saying, is that a safe thing to do? Well, I guess it's safe. It's a weird thing to do. No, it's not a weird thing. It's actually a normal thing to do. And typically that will either print out 6 or 3, depending on which order the bytes of a 4 byte quantity are laid out in memory. We should have it'd be nice to have a SSH connection to a little Indian machine, sorry, a big Indian machine to show you the opposite, but we don't. The MIPS for this is actually nicer. And I guess, and my big point was this C program here to someone who's just finished COMP1521, done well, got a distinction or whatever. This C program is still a confusing mess, I would think. So you're saying, well, how do I help someone who's done well in 1511, worked hard, understood all this stuff, understand what's happening here? One path, and the path we're taking in this course is I'm going to show you what's happening in the CPU and give you a real machine model, and then that will help you understand what's happening in that code. So this is MIPS assembler. I can probably make that a touch bigger. That will help me. No, maybe one down. This is equivalent MIPS assembler. So it sets aside 4 bytes and labels it U. That's the equivalent of that. It then gets, so it gets it loads this value here, loads the address of U, and this sets these 4 bytes to 0x03 04 05 06. But how do the bytes get laid out? Now, we actually specified that in a slide I showed you, but we can test it. So we can test, is the slide correct with this code? The rest is stuff you're seeing in this week's lab. That's just syscalls to print a ASCII value, and the standard stuff to return from a function which we haven't covered yet. So this is the important, just these 4 instructions here can be illuminating. So I get 0x04 05 06 into a register, into T0, and I say store that down here. Then I say load a single byte from the same address. So I'll get the first byte, but what will be in it? Oh wait, no, I can run MIPSy over here. 1521 MIPSy. Oh, tab completion doesn't work for 1521. We should implement that.
More difficult than it sounds, I've tried.
Alright, and it prints out 6. So just these 4 instructions let us explore where the bytes are.
You can probably use H2NS to simulate a big endian byte order if you wanted to attempt that.
Why simulate big endian byte order when I'm currently in the process of turning on a big endian machine?
Jashak has so many pieces of hardware lying about his apartment, which can't be that big, honestly. It must be wall-to-wall hardware.
It's wall-to-wall whiteboards and then the hardware in between, I believe.
Alright, so what we've just seen shows us actually this bit here. There's a choice here about where you put the 4 bytes, and you could have put this one at I+3, I+2, I+1 and I+0, or if you're crazy you could do some fairly random order, and there are mid-endian machines out there apparently that do weird things as well.
Mixed endianness is popular in graphics cards. I have a vague recollection that the Adreno, I don't know if this is necessarily apocryphal or just someone making fun, but I have a vague recollection that the Adreno is just a mixed endian set that looks like Radeon. The Adreno mobile GPUs, I forget who manufactures those or does the IP for those.
Alright. Oh, okay. Alright, that was Indianness. Let's move right on. I know I was recapping that, but it's such an important topic, and I wasn't really happy with my explanation yesterday. So I apologise if you got it. Well, I don't apologise if you got it the first time. I apologise that I had to try and explain it twice, and I just hope you got it the second go. Okay. Yeah. So this is what we do. We say LA register label to get whatever the address is corresponding to the label into the register. Note, this instruction doesn't reference memory. It just gets T7 ready to be used to reference memory. It's getting an address into T7 ready to be used in a load word or store word instruction. So it doesn't access memory. So this we would almost never do. We'd always do the first. We'd let the assembler track that the address is this. It's like a hash define, if you like. It's very like using a hash define. There are some variants of the instruction. You don't need to use them. In fact, at least one of those variants Zach still has to implement for MIPC. Yeah, bits of memory. All right, even a 32-bit address space for most program has all sorts of has far more bytes than we can possibly use, and it's typical. Even though we've got 32 bits of address space, which is 4 gigabytes, there are a lot of computers out there without 4 gigabytes. You're saying, no one buys a laptop without 4 gigabytes these days. That is true. There's not people buying general purpose computers with less than 4 gigabytes. But there are a lot of embedded special purpose computers. The computer inside your toaster might just have 256 bytes of RAM. Probably has more these days. It's probably a whole 4996 bytes or something like that of RAM. So it's very common for the address space not to be, I'd say, fully populated. To be only some parts of it present. And if you access the bits that aren't present, you'll get an error. So, well, the access will fail. So, thinking about it, I'm not really sure what happens at the hardware level if you with an unpopulated address space if you try to access the chips. Interesting question. You can research that. Generally, there's an operating system sitting between us and questions like that. So, to get back to my main point, then as a consequence, we generally pick out areas. You might find me saying segment, but that has a specific meaning that is perhaps not quite what I want. Regions. We generally set aside particular regions of the address space to use for particular purposes. You'll see why more so when we get to functions. But we might put our instructions for our programs starting at that address, from all address 400,000 hex on. So our program might be just 20 or 30 bytes. But we'll put it here, sort of lonely there, running from address 400,000 base 16 to maybe there. So this lonely little 16 bytes, well, let's say our program's 32 bytes. 32 bytes sitting there in the middle of the address space. That's pretty common. It seems a little sad, but there it is. We might put, even though we won't put the data part we're using anywhere near it. We'll put it a long way away. We might put it, say, at that, which is 10 million hex. So our data might be living at 10 million hex to, I don't know, maybe let's suppose we've got 48 bytes of data. So there might be 48 bytes of data there. So that sitting in these two little pockets of this 4 gigabyte address space might be the two parts that our program is using. It's not quite true. There'll be another area of our program we're using, which will be the stack, which will be sitting high in the address space, maybe starting at 7FFFFFFFFFF, which we'll use for function calls. The operating system may itself use other parts of the address space as well. Yeah. So yeah, get used to this idea of the little islands, little regions of this address space that we use, and the rest is just sort of this vast wasteland that's empty. All right. Yeah, global variables. We haven't talked about global variables much. In fact, not only don't we talk about global variables much in 1511, we actually run a program in COMP1511 that says sorry, you can't auto test your program if you put a global variable in there, because we want you to learn to program without using global variables to write proper functions, because it produces so much better programs. But in next week's labs, you'll write code that effectively uses global variables in assembler. So when I'm showing you the C analog, we'll actually show you global variables. What is a global variable? It sits outside a function. I think I've got an example here. Yeah. Alright. So I've set a variable here outside the main function. So if you did this in COMP1511, your tutor would start crying and say, you know, where have I gone wrong that you're doing this? In COMP1521, no, we need to understand the implications of this, and so we'll show you how that translates to assembler. Then when we get to threads, we'll show you why it made your tutor cry, why using global variables is such a problem in terms of program performance and other issues. But still, we have to understand what they are. So this is an example. Yeah, don't write code like this in general. And we'll teach you all the things you need to know. We'll teach you why that is in this course, and also, you know, I guess then it gives you examples of where you might do this. But what does this mean, this array X sitting outside the function? That means that array can be accessed by any function in the program. And this is often students, well, not just students, beginner programmers' eyes light up. This, you mean I can have a variable X and all the functions in my program can access this variable. Yes, you can. And in the end, it's not good. In terms of maintainability, in terms of correctness, in terms of performance, it's bad, and bad. But here's our array X. I've initialized it to 3 values. C, if you don't specify an array size, counts the number of initializers and makes the array that size. That's sort of nice. And down here, I've gone access the array and written stuff out. So, alright, that's my little spiel about global variables. How would this translate into MIPS? Actually, I think I have to go back to. Bear with me. I've got. It's admin. No. Sorry, I showed you this example. That was not the example I wanted to show you. This is a similar example with 3 global variables, X, Y, and Z. This is the first one I wanted to show you because we know how to understand how to do that one. So let me show you how this translates to MIPS, and then we'll get to the array. There, that's the same code. All right. Okay, here on screen. Oh, actually, let me take it down further. On screen is the equivalent of the code on the left. So I've got 3 variables X, Y, and Z. The first thing I have to decide is size. How big are these variables? They're each 4 bytes, so I set aside 4, 4, 4. I say put this in the data segment by saying .data. I could say here, by the way, if I wanted to be super explicit, say .text. Put everything that follows in the text segment, its instructions. SPIM assumes that, but you can actually flip between them. You can say put this in the text segment, now put this in the data segment, now put this in the text segment. you can do that. I'm trying to keep it something simple. We noted yesterday, Dylan was saying, Andrew, I actually prefer to put this up here. I think that's more readable, and I can see his argument there. So you could put, the assembler will handle any of those orders, which is nice. It's also nice, yeah, look, I can use X, Y, and Z, even though their definitions are still to come. MIPS is ahead of C, as some of you noted in the chat yesterday there. You can't do that in one pass. Alright, so what have I got to do? I want to do X equals 17. I've got to get the address for X into a register, 17 into another register, and there is the crucial operation to change X. Same again for Y. That's the equivalent of Y equals 25. That will change Y there. I could actually execute this in QtSpim, couldn't I? And that might be educational, illuminating, helpful. So that's add memory.s, so I can find QtSpim is here and load it. Open that. Alright, so that's just loaded that program into sorry. There we go. We'll put the source up there for you. That message, by the way, was saying, do you really want to do that? Was VI warning me that I was editing the file twice, which I strongly. I don't know how many students I've heard the sad tale of. Oops, I edited my assignment twice from 2 different windows, and I hadn't done backups, and I accidentally destroyed it. Andrew, can I have an extension? Emails. So please take seriously this. When the editor says you're editing this file twice, it usually ends in sadness. I'm not writing to the file, so I'm okay. Alright, this is the code. This is it loaded into QtSpim. You're saying QtSpim doesn't spark joy, Andrew. Well, I've got good news for you. Zach and Shrey have been slaving over WASM and JavaScript and things like that. They're trying to roll out a web-based version of MIPSy that will be so much nicer than this. It's touch and go whether it'll be ready for next week's lab exercises, but they're going to try. So for now, though, we're going to persevere with QtSpim, which is nostalgic in its, I guess, layout. All right. So what do we remember here? I guess one thing we've got to remember is it's showing us the instruction segment of memory here. I can also flip this, if I can see, to show me the other parts of memory as well. What did I say? I said there were. So here's our program. I want to look. This is the address it's been put at. Down to here. So our program is using 90 hex, which is about 125 bytes of RAM. So our program's sitting in 125 bytes of RAM roughly, starting there. So there's a little island of 120 something bytes of RAM starting there, containing the instructions of our program. All among those 4 gigabytes, that vast 4 gigabyte address space, just 128 bytes. You can calculate this as a percentage. 0.0001% is that our little program sitting here at that address. Also in that address space is a place where we're going to store data, which is here. We'll see where that is shortly. Our program is using 12 bytes starting at address 100 million hex. And here's the stack, which we're going to pretend we don't need to know about. Well, we don't need to know about until next week. Okay. if we look here, we can see the comments for our program, and let's actually make this bigger. That would be better. Yeah, that will work better. We can see in the comments, oh, here's our code. Here's my actual code. And here are the real MIPS instruction. Why are they different? In short, pseudo instructions. We write things like li, la, they're not real instructions. Qt-spim shows them as a comment and shows us the real instructions they turn into. It's a lot to get your head around, yeah, I know. It even shows you the byte codes they turn into. And that's even... It's educational to figure those out for one of the instructions, and you should be able to. You know, why does an LUI instruction turn into this? But you don't regularly look at these. It's a bit of a waste of time showing you these. It's not very informative. That really should be something that's there only optionally. Another thing not to panic about is up here. Qt-spim puts code there for not particularly good reasons to get the program started. So there has to be a little bit of wrapper code. The same thing happens with a C program, by the way. You say main, but that's the C compiler has to put extra code in front of main to get the world started. So there's things to set up the execution environment, and then it's called then your main is called. So this is the equivalent for MIPS. Qt-spim has put these instructions here. They're to do with making a function call. Next week's topic. Execution of our program starts here. So I can step with F10. So let me hit F10, showing me the current instruction there, which is doing something with calling main. So this is this code we didn't write. We don't worry about that. We see go to main, and now it's executing our first code over here. And let's try this out. This sets up two registers. Alright, so that's set up register one more, sorry. Alright, so we're at this instruction here, the store word that's storing whatever's in register T0 to the address that's in T1. So the 4 bytes of register T0 will go to the address at T1, the bytes at that plus 0, 1, 2, 3. We'll write 4 bytes to RAM. Now if we look over here, we should see, it's not the most beautiful, it's far from the most beautiful or clear description of RAM, but we should see the RAM change here when I execute the next instruction. When I execute that circled store word instruction, we should see those bytes change. Please change. And there we change. You're saying that doesn't make a lot of sense to me, Andrew. No, it doesn't make it's not the easiest to understand, but there it is written there. You're saying, wait, 11. I wanted to store 17, but of course 11 hex is 17. All right, if we execute a bit more, we should see 25 get written there. And there it is, 25, 19 hex is 25. That gets written there. Now let's flip back to showing you the text segment. This is what we're talking about. This is what happens on a reduced instruction set computer. This is the epitome of the difference between RISC and CISC, between a complex instruction set computer and a reduced instruction set computer. There are computers where a single instruction can specify get value 1 from this address, get value 2 from RAM from this address, compute their sum and store it back to address 3. So that can be done in a single instruction. Here it is at least 7 instructions. In fact, some of these are pseudo instructions that expand into multiple instructions, so it's probably 10 instructions. He's saying, that doesn't seem good to me. It's good in terms of making the instructions themselves simpler. That's good in terms of making building the silicon itself simpler. It's good in terms of writing compilers, how to write good compilers for the architecture as well. So there are wins and it's a balancing thing. Now, all right. By the way, if you want to get into CPU design, there's a complicated world then underneath what happens in complex instruction set computers with things like microcode, which are far beyond what we can talk about in this course. Let's execute it through all of this, and let's see if we can do it. See a load instruction happening, and then we can move on. All right. So we're set up for a load instruction. We're set up for this load instruction here. So it says load whatever's in register. Use this address. This is the offset I talked about. That says get that address and then add this value to it. For a lot of the coding we do, we'll add nothing to it, so that value is 0, and put the result in register 9. So we should see that register 9 changed to whatever value that should be. Seems to have a value in it already. Alright, so let's execute that and see it pop in, and there we go. So there you saw register 9 get the fetch value from memory, and you can look at memory and see that fetch value, and it came from there. You're saying this interface could be clearer. Yeah, we've got it's a bit of a low bar, but we're confident that the web version of MIPC will give you a nicer way to look at this stuff. It's not without so much mess in front of you. I don't mind so much. It's a constant in dealing with systems and computers that you've got to get good at picking out from a whole array of information the few bits that really matter. It's a struggle. It's a skill. You know, some people just can't cope with not knowing what a status value is or what these values here are down here, and they don't do well faced with this sort of thing. You've got to be able to say, put it out of mind. Well, I don't know what that is. I don't know what this is, but I know what this is, and I know what that is, and I know what that is, and focus on what you know rather than what you don't know in dealing with interfaces like this. If it's any consolation, generations of students, computing students around the world have done this before you and survived and gone on to do wonderful things. All right, let's change then. Let's look at doing the same for an array. Oh, I'll run this through just for. We'll switch back.
There was a question in chat which I saw a couple of times, which is about type. What type is the dot space for?
Ah, what a great question. What type's it for? So there are no types. We are beyond the world of types. All we have are bytes. So yeah, so types are really relevant here. So what I need to know is how many bytes to store for x. In C terms, that would be size of x. So sure, the type for x is relevant in that I need to know how many bytes, and that's a consequence of what type x is. If x is a double, I might need 8 bytes. If it's a char, I need 1 byte. If it's an int, it's 4 bytes. If it's an array, it could be 1,000 bytes or 1,000,000 bytes. But excellent question. Yes, so types are all a thing of the compiler. By the time we get to assembler, types are all gone, which is why assembler programming is to be avoided at all costs, because types, you may not realize it, but types are so much your friends. There's just these vast class of errors that you never have to worry about if you use the type system well. They're detected instantly for you by the type system. Lose the type system and suddenly you've got to debug all of those errors the hard way. So
There,
yeah,
there
thank
are
you for that
the
question.
fundamentals of signed and unsigned still exist, but not with the memory. It's to do with what instructions you use to access the memory. So saying this piece of memory is signed or unsigned depends on what instruction you're using to access it, and that's pretty much it. Apart from that, you just have bytes. You can use the bytes for whatever you want.
So you're right. There's still the question of representation. Yeah, I've got those bytes. Well, what do they mean? There's not many possibilities that matter at the assembler level, but signed versus unsigned is a big one at the assembler level. The operations, so we may need to use different instructions at the assembler level for unsigned ints versus signed ints. And floating point would be another one. Yeah, floating point's another good example of where there are instructions. But outside that, do these bytes contain, the bits of a JPEG, of a video, of a PDF? That's way beyond where we are at the assembler level.
I guess you do have a single distinction between floating point and non-floating point. In MIPS, there are special registers just for floating point integers, which we don't really touch in this course. But you know if you're touching a floating point register because it starts with $F number, and that's specifically for floating point numbers.
And I can see someone slagging off Python typing in the chat. It could be Jashank under an alias, actually. But has anyone seen Matthew Richards and Jashank in the same room?
I'm pretty sure Jashank's too busy compiling a driver right now for internet access.
No, just a user that can log in.
So yes, types and some languages like Python, it's an interesting concept. There are all sorts of ideas about typing. There are complex ideas about typing, and Python's typing is mainly dynamic. Entirely dynamic? There is some static
Python
typing.
Does have a type system.
They
Python
added
does
some
have a
static
type system.
typing.
It's just that you can change it at any point. You can reassign a variable and it reassigns the type. But every value has a type associated with it. It's not that types don't exist. They are there.
It's more the functions and types that get interesting in Python. But anyway, all right, we can't venture into that area because we've got to venture into arrays and how they work. All right. So my next question was, let me bear with me. I get that, and then I go to this. I've got an array. How does that work with load and store? So I've got it's the same program as before. We've initialized the array like that. How does that turn into assembler? Let me show you. No, this is the same program as previously. This is using the initialization. I can do this. So this is a slightly different example. Sorry, I'm trying to go through this slowly and carefully, making sure everyone understands it. There we go. Our previous program just said X was 4 bytes uninitialized, 4 bytes uninitialized, 4 bytes uninitialized, and it used store word instructions to store values 17 and 25 into X and Y. So I put 17 and 25 into X and Y. We didn't have to do that because we could have said .word 17. A .word says set aside space for these 4 byte values, and I've only specified one, so it'll be just one lot of 4 bytes, and initialize the first one to 17. Similarly, Y says set aside space for the same, initialize that to 25, and that avoids those instructions. And then the programs are the same. So that's showing you use of initialized memory. Sorry, I don't know if I've got. Well, how would that look in C? Let me go back. I wanted to show you what it looks like in C. The C equivalent is here. In C, this would look like x equals 17, int y equals 25, and int z. So that's how it would look in C. If you wrote that in C, it would translate into something like, the compiler would produce something that looks like that. Note, these are global variables created once. They're not local variables in a function. We'll see those still to come, but that's sort of the equivalence MIPS to C. So what about this? What does that look like in assembler? How do you do an array index? Alright, here's one way to do it, but it doesn't generalize, so we're going to need to work out more. So I've said, look down here, this is nice actually, yeah, it is nice, it shows you one thing. This sets aside 12 bytes. I've said dot word, which means 4-byte quantities. You're saying, why isn't it something descriptive like dot int 32? Yeah, that would be perhaps smarter. Dot word, and then 3 values, so 12 bytes, which get initialized to 17, 25, and 0. When I want to access the first, I say 0 as my offset. The second, I say 4 as my offset. The third, I say 8 as my offset. Why 4 and 8? When my index is... oh, that code is... it really is not good there, Andrew. What we wanted. Why 4 and 8? Because when I want to store at array element 2, I need to be 8 bytes on, because array element 0 is 4 bytes, array element 1 is 4 bytes, so 2 times 4 is 8. So if I want to get to the third array element to store the value, I have to go at an offset at 8. Similarly, if I want to get to the second array element to get its value, I have to get over the first array element of 4 bytes, so I have to add 4. To get at the first array element, it's 0. So this is a simple use of this offset on the addressing to say, look, I've got X here. I've got the address of this of the first of the 12 bytes in register T0. I can go from there. Now, you're saying, that's array elements done. No, it's not. It's certainly not, because this only works because these values are constant. They're not I or j times 3. And you've already written lots of programs where your array elements are calculated from variables. So this simple approach is great as long as you're accessing array element 1 or 3 or something like that. You can calculate a constant offset. And where does this offset go? Go back. Go back. Further back. This offset goes here in the load word, or here in the store word. Alright. But still, nice example. we're nearing time. I want to show you something to think about while we have a break, though. Not that one, though. Maybe this program. I'll show you 2 C programs and then we'll have a break. Maybe more C programs, we'll see. So there's a messy program. What does this do? This creates a double array of size 10. 80 bytes. 8 bytes for 1, 10 by 8, 80. It prints out the address in memory of each of these array elements, and then shows you how this address would be calculated. You're saying, Andrew, this program is horrible. Yeah, this is not a program for this is a program for running rather than reading. So let me compile it for you. And run it and see if it is illuminating. This is code that's meant to explain something to us. Alright, and it does. Look there. There are the elements, the addresses of the array elements in hexadecimal. And you're saying, oh, look at that, Andrew. They're each 8 more, each one is 8 more than the next one. And C guarantees that. Array elements sit snugly beside each other in memory. They're not, arranged in reverse order or flipped about, or there's not huge gaps left between array element 3 and 4. C actually tells you that array elements are laid consecutively in memory. So we can, and that should make sense. If this is where the first is the address of the first of the array elements, 8 bytes on, 8 bytes on, 8 bytes on. This then lets me do my own address calculations. If I know the address of the first array element and I want the address of array element 7, then all I have to do is get size of the array element and do the calculation. So this is just showing you that this is the address of array element 7. Is it correct? Let's try it out. Sorry, array element index 7. So it's the address of the start of the array times 7 times the size of the double, which is 7 times 8, which is this address plus 7 times 8. And if you do that calculation, it's showing you this. So here's our fundamental thing. This is demonstrating a fundamental thing is if I want to get an array element X, what I really need to know is the size of an individual array element. And then I can do 7 times, then, well, X, to get array element X, I do X times the size of one array element. And add that to the address of the first array element, and I can do my own array indexing. You're saying, really? You can do away with square brackets? Yes, I can do away with square brackets. I no longer need square brackets. I can do everything with pointers. I've moved this, the array outside, and I've initialized it.
Can I just put a PSA here and say, just please don't do everything with pointer arithmetic in C. All
right. So you know how we said
brackets.
You can do all these loops with goto. There was a clear caveat that no, you should not do that. The same would apply here. Using square brackets to do the array indexing for you, a great thing. Makes your programs much more compact and readable, but still, we can do this. So I want to get at array element, the array element at index 7 here. So I want to get it at the array element, which is that one, 17. How do I do that without using square brackets? Alright, so I get the start address of the array and put it in a value I. Don't worry about that type there. It's a type coming out of student. It's a weird type to say you want to do integer calculations with a pointer value, use this type. Not used for regular programming. I get the size of one array element, multiply it by the index I want, add it to that value, get that value and turn it back into a regular pointer to that array, put it in say y, and then print it out. So this code should print 17 out. Let's try it out and then we'll have a break. If this works, I'll show you the assembler, put up that, and then we'll have a break. Look at that. So I've managed to access 7 of the array without, there are no square brackets. No square brackets in my program. You're saying, Andrew, you could have just written array 7. That was Dylan's point, really. Yes, just do that. But this is showing you what the square brackets are doing. So this is showing you what the square brackets are doing. Don't worry about the code to come, and don't worry about that. We'll come back to that. I think I've got this in assembler for you. We've seen that. Oh, we've seen, yeah.
You do technically have size of array square bracket 0, which you could rewrite as size of star array to get rid of all of your square brackets.
That's just nitpicking. All right, I don't have an assembler equivalent. All right, this is a good time to take a break. So don't worry, we're going to talk more about array indexing. This on the left is sort of generic assembler to do an array indexing, so you can try and read that during the break if you like. So, but I need a short break, so 5-minute break, everyone, and get up, stretch, bathroom, whatever, refocus your eyes. We'll be back in 5 minutes. All right. Welcome back, everyone. I see in the chat there people are saying, "Yeah, Andrew, you're not helping here. This is scary, and I don't understand." Well, I'd say a couple of things. One is have faith. So many students have come through this course and understood this stuff, so you will too. Second is there are lots of resources out here. So if listening to me, trying to explain it is not working for you, there's plenty of alternatives. I'm not going to be hurt if you learn this stuff from someone else. Also, we'll be practicing it with lab exercises, actually doing these things, and often that's the best way to learn these things. So, but I'm going to keep trying to explain this stuff to you. All right, let's try some simple examples. I got this C. I've got a 10-element array, 40 bytes. Look down here, 40 bytes, not initialized. So I've just said dot space, 40 bytes. And as we said, yeah, up here there's a type, down here nothing, it's just 40 bytes. And a thought might be occurring to you, I've got some great ideas for a new programming language. You mean if I can just have write my own compiler that produces this, I've got a programming language implementation. Yeah, it's one way to implement a programming language for sure. Take in something like that, put out something like this. And you can have your own types, your own type system, your own data structures. What I would recommend instead, by the way, is you're building your own. If you want a compiled language, I would compile to C or something similar to C. You'll find that easier to experiment with your language.
LLVM.
And Zach's saying LLVM, which is a whole, which is just for that sort of purpose. So if you've got programming languages dreams, Google LLVM but be prepared for a little bit of investment time to get across what LLVM does. So save it until after the exams, please. And definitely after you've passed your maths exams. All right. So 3-element array. The crucial thing I need to know is I need to know 3 things. The address of the start of the array. Where in memory does the array start? How big is a single array element? And the third thing is what index? And that leads me to a calculation. So it's 3 times array element size, and then add that to the start. How does that happen over here? We get the 3. This is the size of the array element, so we do a multiplication. So we've got the first part of the calculation there. X has got the start of the array. We put that in T1, add them all together, and we finish up with the address of the array element we want in T2. We're doing a store operation here, so we whack the value we want to store into T3. And here's where we actually access memory. These instructions are all just instructions. Everything's just in the instructions. They don't access memory. Here's the store word instruction that actually changes memory, and it says store what's in register T3 to the address in T2. Notice the constant offset there. It's useless to us here. Well, I guess we could pre-compute this if you wanted, but in general, that doesn't help us because it's not fixed when we were actually writing the program. It's a calculation that depends on other things, and we instead have to do an add. All right, so that's storing a value in an array element. Let's change things up. Let's make the array element 2 bytes in size. 2 bytes. And the array is size 30, so we should be setting a size 60. Yeah, got that right. The array is still starting at x, whatever x is. We're still loading x in there. Our calculation will change. We're accessing array element 13, so we do 13 multiplied by 2 and add it to x, and store there using a sh instruction because we're storing a 16-bit quantity. So that's the same thing, just with different values, different parameters, if you like. Same pattern, different parameters, just verifying you understand the pattern. Okay. printing an array. Yeah, this gets more interesting. Alright, this is showing you printing out an array. The array is off screen here, it's numbers. Well, it's probably in. Well, I can show it to you. Is that the better way to do it? Probably is. There. So we've got C code that looks like that. We can compile it and run it and demonstrate to you that it works. Print 5.c. And there we go, printing out the 5 numbers. Yeah, that code works. Lovely. Now, you could try taking that straight to assembler. That's fine, but you've seen my technique is to go halfway, go to ugly. Oh, sorry. Is to simplify the individual statements in the C. As someone pointed out in the chat yesterday, Andrew, this program's so much harder to read. The program's not simple. It's true, the program's not simple, but what each line in the program does is simple. So each one of these things is simple and can be simply converted. We've made the program ugly, though we can still verify the program does the same thing. As computer scientists, that's the difference between us and the mathematicians here. We work where we can execute things in general, so we can check things by executing. So I can check that I've transformed this into a program that does the same thing. This is the luxury that poor mathematicians don't have. I've got a program that does the same thing, and now I can whack that over into assembler, and away I go. Hopefully. Oh no, we didn't. Oh, sorry, I've got confused here. Oh, have I? Bear with me. There we go. That's the assembler. I was a little bit worried there. Yeah. Wait, forget you saw that one. That was the next one was a spoiler. That assembler just flashed on the screen. So let's look at what's happening here. And I've said everything translates pretty simply, and that's not exactly true, is it? That's our standard finisher function. That's okay. The loop. Those of you who've done this week's lab, I'm hoping the loop looks okay. That's probably better written as a B. It doesn't make a lot of difference. That goes back up to the top. The top says if t0 is greater than or equal to 5, go to end. Yeah, that's a good implementation of a while loop, we think. The key thing is to track that I is in t0, and you might read through that and make sure, does anything muck with t0? No, I can't see t0 mentioned anywhere. So that looks like a good while loop. So you read that code and think, yeah, that looks like to me it executes the loop 5 times. That's nice. Then what? We've got to do this address calculation. We've got to get the address of numbers I. So I is in t0. So the address will be that times the size of an array element plus the start of the array. An array element here is 4 bytes. So I is in t0. So that's I times 4. Put the result in temporary register T2. Now, if I was a good coder, I would have noted up here registers T2, T3 being used for temporary values, perhaps. The more you can note in comments and track what registers are used for, the happier your life as an assembler program will be. And then, again, it's not great commenting, but I get this is the start of the address of the array. I add it to the calculation I did of I times 4, and that's the address of the array element I want to load. I load it there into A0. which conveniently is where the syscall wants the integer to print. And then I do system call 1, so that's setting up for the system call. You'll remember V0, every system call, what the code behind the system call, what the operating system behind the system call does is the first thing it looks at is V0 to see which system call you're asking for, and then some system calls need extra information, and a print integer system call needs to know what integer to print, and that's in A0. If I've got all of that right, if this will execute it. Let's run it in MIPC. And there we go. Run in MIPC. Curious. We might try stepping through that in MIPC. Just indulge me. So I'll start MIPC. I might just step through it. Load. Oh, tab completion is not my friend. So that's the MIPC startup code popping out there. That's initializing I to 0. That's checking the loop condition at the very top. Yeah, this is where things get confusing, isn't it? I said, it's a bit hard to read in the MIPC there, I said branch $t05 end. MIPC's got to turn that into two instructions. One of that is that, and the next will be that. So my BGE instruction branch, oh no, it's 3. My apologies. My BGE instruction here turns into these 3 real instructions. If you're finding all of this, you're understanding this, you're with me, then I'd make sure you know how you can understand, you can go and figure out why that does what it does. They sort of, yeah, they don't make sense in a human terms, do they? You think, why am I doing an OR instruction? And why an OR with 0, which does nothing? Yeah, well, it's just a way to get this value into this register. Alright, so that's the thing at the top of the loop. That should be false for the first 5 times, so that branch should not be executed. Let's see if the branch is executed, or do we finish up just executing the next instruction? Look, well, we did. Why did we? Oh, I'm sorry, yeah, I'm reading the wrong thing. This in lovely green is the information we don't really care about, which is the encoding of the instruction, and in grey here, Zach, is the crucial address. You should have a word to Sasha about human factors and interface design there, I think. Alright, so side note, Sasha is she's lecturing 1511 this term, but she's lecturing human computer interaction COMP1521. Of course, I'd highly recommend it if you're interested in designing programs that work well with users, and focusing on, you know, what's communicated and what's emphasized and what not emphasized. To be fair to Zach, the coloring of this stuff has been done very quickly in a quite a simple hack, which I think he's going to revisit and do in a more principled way. But the crucial thing here, well, so I guess my message to you is, if you're sort of interested in that sort of thing, pencil COMP1511 in your future courses to take. And the other thing would be, look here, this is the instructions address. So this is the encoding of the instruction. It's nice to understand once or twice, but most of the time we don't care. And we've gone on to the next instruction. So we've gone from 400C to 40010. So that's 4 on. And we can keep executing through the program and doing an address calculation. And again, here we're seeing pseudo instructions. The multiply here is turning into 4 pseudo instructions. It's a little scary, isn't it? No, 3 pseudo instructions. we finally get to our first load, which is going to access memory and get the integer to print. Now we can say print, I can say print, is it $all, and it should show us, I probably could have, should have said print T3, shouldn't I? To see what address I'm going to load. Oh, there we, oh, it's in decimal. That's the address we're going to load. There. It's a nice example of why. So for the loop counter for I, which is in T0, decimal is great. For addresses, not so much fun. Addresses are more conveniently in hex. That's sort of
So
nice.
you should just be able to do print T3 space hex or X or something like that.
Oh, look at that. All right, so that's thank you, Zach, for that helpful hint for students using MIPSy. B, that's a perfect example. T3 contains an address, and it doesn't make a lot of sense as a decimal number, but here we can see, oh, it's right at that start of that little area of memory we use for data. So that's quite nice. Oh, so can I say print $all x to get everything in? Oh, I can't. Oh, isn't that beautiful? I guess. And if you're thinking, oh God, I'm still not comfortable with hex, sorry, that's one of the things of this course. You've got to be comfortable. Decimal, hex, binary. You can't work in this sort of space without being comfortable with moving between them. Your life will be better. Just embrace it. All right. Oh, how do I print RAM in MIPSy?
You should just be able to type in an address or a label or sort of anything like that.
Oh, a label. So you say I can say print numbers. Oh, look at that. Can I say print numbers plus 4? No.
I don't know if you can. You could do labels. We'll give you the address of all your the addresses of all your labels, and you could do the the math in your head. Like just run a command labels or ls for short.
Oh, there we go. So can I print ranges with 2 values?
I can't remember. This command was written in probably 20 minutes. Maybe
All right.
9
What I
months
can
ago.
do is just so I can poke at memory addresses like that. Well, except not
Sure
like that. I
can.
can't. So I can see. So what's that 1B you're saying? It's the 27 there. 27 is 16 plus 11. 1B. Obvious. Some of you are saying yes. Some are saying I don't want to be that sort of person. But yes, you have to be that sort of person. And there we go. 51 hex, which is 81 decimal, which is there. Lovely. All right. So what I found out was where X unlabeled. Oh no, it's numbers in this program. By the way, Zach is taking feature requests either in the course forum or at the MIPSy GitHub. If you've got ideas about improving this, if you're a COMP1521 student and there's a feature you want here, you just put in that feature request to Zach. I'm not guaranteeing you'll implement it, but he's actually eager to get feedback about what MIPSy should do. What would be so this? It's all meant to be a tool to help students. So if there's something you think would help students, you let us know. No, don't let me know. Let Zach know. All right. Okay. That was a nice program. I think I've got a different sort of program to show you. We saw that. Printing an array, we saw that. Printing array, we saw that. Oh. I have a different way to print an array. It's a weird C program, isn't it? I'm using pointers to print an array. And again, this is sort of maybe weird and scary. as someone who's done one programming course. But if you can understand MIPS addressing, and then see the MIPS addressing for this and how it works on the MIPS, suddenly the C code will stop being weird and scary. I should caution you, there's a step that far too many people make. They understand how this works on the assembler and then assume that's how C works everywhere. You've got to be careful about, then if you want to write a C program that works everywhere, you have to look at what the C standard guarantees. But that's sort of a meta issue we don't have to worry about yet. You have to worry about in a year or two's time. There. Alright, so what do I do? I've said make P point at the first array element, make Q point at the last array element, then while P less than Q. If you've got pointers into an array, you can compare them using the usual comparison operator, and if P points to an array element before Q or the same as Q, that loop will keep executing. That's great. That'll print out whatever array element P points to. Yeah, so there's two huge things here with array elements and pointers. If, and this is a big if, and this is something that people sometimes forget, if P and Q point into the same array, then these two operations, then you can do a comparison operator. Similarly, if P points into an array and is not pointing at the last element of the array, saying P++, adding 1 to P will take you to the next array element. So P will point at the next array element. P minus will take you point you at the previous array element as long as it exists. P plus integer will take you that many elements on. P minus integer will take you that many elements back. All though are only correct, only defined if P remains pointing at a valid array element. So this code will print out an array. I've turned it over there into the simplified thing, but that really just breaks the loop down. It doesn't change the really interesting operations there. Let me demonstrate to you that this code works by I think I have to, where are we? No. Yeah, there's the code. Alright. Let me compile it and demonstrate it works. .x. Thank you, Andrew. That's better. Now, I know there's some of you saying, but why? I like the old code. I understood that code. That was gentle, that was friendly. I understood this code. Is there any reason to use your weird, scary code? No, not really. So sometimes people think there's something better about code like this, and the answer is no, not really. The compiler is probably equally comfortable with both, and this first version, this is probably actually I'll put it side by side. It's an important point. So yes, I know. Edit it anyway. So I've got them side by side. So sometimes people think, oh, pointers are great, this will run faster. Generally, compilers are smart. The compiler will take both those pieces of code and produce the same assembler. So the end result will be same execution speed. Which then is more readable, which is more maintainable, which is more obviously correct. And I think this one, and this one. So yes, the code you've been writing, better. Don't use code like this unless there's a reason. There can be reasons, but you don't have to abandon this simple, safe, comfortable code that you've been writing since 1511. Except This is not a lecture about how to write out an array. This is a lecture about how to understand how addressing works on a computer. So we want to see all of these things working, even if you're not really going to be writing this sort of code. So it's not about making you a better programmer. It's about improving your understanding of what's happening in a computer. You understand pointer addressing. Now, it's quite possible you'll encounter code written in this style. There are plenty of C programmers, me included, who are very comfortable with pointers, will happily churn out code that looks like this and much more complicated. And you may end up, effectively you may end up in, say, summer intern, and the boss says, oh, we've got Andrew's code from 20 years ago. Can you go in there and rewrite it and make it readable and maintainable for me, please? So you may need to get code like this and understand it and fix it. All right. So I've demonstrated that works. How does that? We'll even go to the simplified version. It doesn't really simplify the pointer operations, though, does it? So that's what we've got for the simplified version, but we've still got to translate that to assembler, and I have that here for you. Not there, but it must be the next one. Oh, no. All right. Oh, this assembler's got a bug in it. That's really weird. Oh, no. Okay. It's sort of got a bug in it. It's a bit weird. I guess that'll do. Alright. So I want P pointing at the start of the array. So I say the arrays. Let me make this a bit. The arrays address numbers. So I say load numbers into T0 and P's in T0. Yeah. I've said Q's in T1. Okay. I want Q to point at element 4 of the array. Each array element is size 16, so if I add 16 to T0, which contains the start of the array, that will have T1 pointing to the last element in the array. My comparison suddenly it doesn't matter. I'm doing a comparison with pointers. So there's a lot of meaning in C with greater than and is it an integer, is it a pointer? All of that's gone, and a greater than does the right thing for me. On the MIPS, that's sort of a general thing. On some computers, that would break outside an individual array. Here, when I want to say load from the address P's at, I just say load from T0, put it in A0, print it out, go around, and here's the pointer arithmetic. So if P's a pointer to an array, how do I make it point to the next element of the array? If P contains the address of an array element, how do I make it point to the next one? I just add whatever the size of the array is. So in this case it's 4. If it's an array of doubles, this would be 8. If it's an array of structs that were each 300 in bytes in size, that would be add 300. So what this is number of bytes of the array element. And that would
there's some stuff in the chat, Andrew, which is a great question. People seem to be happy about the MIPS having P plus equals 4, or add I T0 T0 4, but are wondering why the C code has P plus plus and not P plus equals 4.
Yeah. Excellent question. So that's how pointer arithmetic is done. Yeah, it's strange. the designer of C, Dennis Ritchie, said, "Oh, what does it mean to add to a pointer?" And this was the meaning he came up with. If you add 1 to a pointer, you move to the next array element. Now he could, and it was a good choice. The alternative would have to be, then you would have, if you didn't have that, and if it added bytes to the pointer, you then would have to say p plus equals size of, well, you could say star p actually, but you'd have to have a more complicated thing there. So that was the first thing he realized, was if adding to a pointer just added bytes to the pointer, that you'd need to do this to move to the next thing in an array. The other thing you realize is that you'd always want to do this, that you'd almost never want to move an integer pointer on just 1 or 3. What does that do? Well, that leaves you halfway through the next integer. So you're always going to want to move a whole number of the size of the thing you're pointing at. So yeah, this plus plus.
Recommend, Andrew, that you, in your MIPS code, you change that 4 to a 1 and see what is possibly the most common error in MIPS programming and how SPIM and MIPSy handle that error.
MIPSy doesn't handle that error particularly well.
Oh,
right
good.
now,
We'll show that then. We're
I
going
mean,
to break MIPSy on screen.
MIPSy doesn't care about alignment. MIPSy will just let you go ahead.
All right. Okay. Actually, let's look at this. All right. So that plus plus. What that means is the C compiler then has to look at what type P is. And there's a thing, you're talking to students when they first talk about pointers. You say, what type is P? And they say, oh, it's a pointer. Well, that's incomplete information. Pointer isn't a type in C. Pointer to int is a type in C. So you have to know that's the full type of P. And so if you do plus plus, that moves P to point to the next element of an array, and it's only defined if P points at an array of int. All right, so let's show, if we somehow forget and make this plus 1 in our code here. Well, actually, we should make sure this code works at all. So 1 for spim minus, we'll try that with spim and it's pointer5.s. Let's see if it works. Yes, spim does the right thing. MIPSy does the right thing, please MIPSy. Oh, all right. Now let's break the code. What does spim do with it? Now spim is giving me this message, which expect to see this in your auto tests next week. If you get your addresses wrong, this is often how it manifests. We're attempting to load a 4-byte quantity from an address that's not divisible by 4. Is that possible? Yeah, it sort of depends. Spim says no, it's impossible. There are various implementations of this. There are sort of complex issues surrounding it. Generally, we try and keep bytes aligned to their size. Sorry, loads and stores aligned to their size. So if we load a 4-byte quantity, we try and do it from an address that's divisible by 4. For an 8-byte quantity, we might do it from an address divisible by 8. Beyond there, it probably doesn't matter. 1-byte quantities, you can load from any address. 2-byte quantities, an even address. So spim's saying, Andrew, you tried to load a 4-byte quantity, but your address was not divisible by 4. That's printing out the address there and saying, Andrew, that's broken.
Something important here is if you install spim at home, I don't think you'll get the same error message. I think 1521 SPIM has been modified slightly. I believe the original error message is unaligned access occurred and ignored, and then it will just continue running. I believe
Whoa.
that is a modification we've
Yeah,
made.
I think that's right.
And Mipsy.
And Mipsy doesn't care.
All right.
Mipsy doesn't
Okay.
care yet.
Yeah, we will fix that. So the real world is complicated there. There's some hardware where this is an absolute, and if you try and load a 4-byte quantity from an address that's not divisible by 4, the hardware won't do it. Though to make things more interesting, the operating system may then get the error, intercept it, load everything as 1-byte quantities, put them together for you, and go back to doing what you were doing, pretending it never happened. You will notice though, because then your program will run about 10 times slower. And there's other hardware out there these days where there's little performance penalty for doing loads that are not on boundaries, unaligned loads. Intel processors have changed drastically in that. It's gone from like slowing your code down by a factor of 10 to maybe slowing it down by a couple of percent. Alright, let's not worry too much about that. I had one more thing with this pointer stuff. I had a faster version of this, didn't I? What was the faster version? How have I made it faster? I'll put it up here maybe. I've done a little bit of optimization. Is that useful? I'm trying to remember what I did here. Is that interesting? Not particularly. I've reversed the loops. I don't think that's very attractive. All right, let's ignore that. All right. Let's get back to some lecture slides. That's printing a 1D array. All right. That's interesting. We've got a C program that does the same thing, that does an unaligned access. Oh, look at this. Again, this is code that is a real struggle to understand from what's seen in 1511. But it says, oh look, give me 32 bytes. Alright, give me a pointer to the 1 byte in and pretend that points at a 4-byte quantity. Then try and store something at that 4-byte quantity. And let's see what happens. What does happen there? Well, let's do that down here. DCC says, Andrew, that looks like a silly thing to do. Yes, I know what I'm doing though, DCC. And it dies. Look at that. So I think the C standard actually specifies, because there are machines out there that depend, I've talked about how some machines break entirely. If you try and store a 4-byte quantity at an address that's not divisible by 4, or a 2-byte quantity at an address not divisible by 2, or an 8-byte quantity at an address not divisible by 8, the C standard says you have to do that. So any C implementation can depend on you doing that.
Should
And
that
here
not be
I've...
ref bytes of 1?
Sorry?
Should that not be ref bytes of 1 casted to an int star?
Yes, it should. So how does that work?
I think is that like a weird poison value? 000B?
Yes, it is. Ah, well spotted, Zach. All right. So
That
that's
smells
sort of
like address sanitizer to me.
it. Yes. Well, it's my code actually. That's I'm using that, but I've chosen that because it's the same. But that's DCC putting that BE in there. All right. Huh. That makes no difference to the error, but yes, that code was, the example was completely broken. Thank you, Zach, for spotting that. All right, so that says get the address, get that address, and do a store, and that's not defined. Let me show you perhaps a more comprehensive example of that to wrap up with. We'll recap this a little. What happens if I got a pointer from malloc? I don't know. I get a pile of memory from malloc, and say do the same thing. Go 1 byte into the pile of memory from malloc, and what happens? Oh, you've got to declare malloc. I'll get the same error. And I'll get the same error. Now, I've done this deliberately, so, but this will always work. So I won't get an error there. If I take a pile of malloc, get memory from malloc, and use it, oh, that's fine. That's a different problem. So malloc always gives me memory that's aligned. You can try that out. You can get oh, yeah, we'll finish with that. That'd be a nice program to finish with. We'll ask malloc for 256 bytes of memory, and then we'll print it out, what the address is we've got from it, and look at what values we're getting. Oh, it's always, oh, interesting. So DCC must turn off malloc randomization. Alright, I can fix that though. Put this in a loop. Recompile that. You can see the addresses malloc's giving back. Are they divisible by 2? Are they divisible by 4? Are they divisible by 8? Yes, they are. You're saying, well, maybe it's because you're asking for 256. Yeah, fair point. What's a large prime number? Is it 153 prime? Don't honestly know. Let's try that. Malloc's still always giving me addresses divisible by 2, 4, 8, 16. They look like, in fact, they're divisible by 32. So malloc knows that I might be putting an int array in it, a double array in it, so it avoids this unaligned access error. All right. Yeah, 64-bit alignment, I think, is someone suggesting, and someone else is pointing out to me that 153 is not prime. Okay, I acknowledge that. All right. Sorry, we're out of time here. There was a bit more on to say about aligned accesses, so we'll recap aligned accesses and a bit about arrays, and do 2D arrays at the start of next Tuesday's lecture. Enjoy this week's lab exercises, which hopefully will grapple with simpler things for you, with branches and registers and syscalls. So thank you all for tuning in. I will see you all next week. Well, sadly I won't see you, but next week we will chat.